Hello students, today is going to be the last subject matter for the 2019-2020 school year.
Oh yeah!
We're going to look at ionic bonding. Now, in order to get the credit for this assignment, you're going to need a piece of paper, and all you'll need to do is follow along, writing down everything that you're going to see in the video on your paper. You take a nice clean snapshot of your work. You submit that to Schoology, and you're guaranteed an easy 100% to finish the school year with a nice, easy grade. So let's start off with this. We have two elements. We have lithium and we have fluorine. Both of these two elements are chemically unstable by themselves. Why is that? Because lithium has only one valence electron. It's an alkali metal. It's chemically unstable, reacts readily when it's thrown into water. Because it does not have a filled outer shell. Fluorine, it's a halogen. It's in group 7A. It has 7 valence electrons, and it is missing one electron right here in order for it to be chemically stable. All right, so how do we know if these two things are going to react with each other? What we need to do is we need to look at the periodic trend called electronegativity to see what's going to happen when these two things do interact. See, electronegativity is that relative attraction that an element has to pull electrons towards it when forming a compound. So fluorine is the most attractive element on the periodic table. It has an electronegative value of 4. Lithium, on the other hand, it only has an electronegative value of 1. So when these two things interact with each other, what we do is we subtract those two values and we get a change in electronegativity of 3. We compare that to the chart that's on the back of the periodic table. If we see the electronegative value for this is change in electronegative value of this is 3, that means that fluorine is so attractive that it's going to pull this electron away from it. When these two things react, it's going to pull it away, and now fluorine has that missing electron that it needed to gain to get an octet or 8 electrons. Okay, so now fluorine is chemically stable. What about lithium? Well, lithium, now that it's gotten rid of this outer 1 valence electron, how many does it have now? Lithium has 2 valence electrons. So you might say, wait, you've said in previous videos that we need to have an octet of electrons for things to be chemically stable. Well, that is true for almost all elements, but lithium, it doesn't have but that one energy level right now, that first energy level, and how many electrons can fit there? 2. So now we do have a filled shell. It may not have 8, but it's a filled shell now. So that outermost electron came from this outer ring, this valence shell. That electron was attracted to the fluorine like that. Okay. So what did we form here? This is called a lithium fluoride compound. All right. Now, let's move on to some other ones. We will not do any more Bohr models. Okay, so it's going to be easier after this. I just wanted to explain what was going to happen here. Okay, our next example, I want you to make sure you have these in columns now. We're going to have reactions here. So that's going to be the title of this column. We're going to have lithium and we're going to have chlorine this time that are going to react with each other. Now, lithium, its electronegative value is a 1. Chlorine is an electronegative value of 3. If we subtract these two values, what we get is a change in electronegativity of 2. Okay, so that change in electronegativity is 2. That tells me that this is going to form an ionic bond. So lithium, it starts out, now this is called a Lewis diagram. We're only going to put the outermost electrons for this. We know lithium has 1 valence electron. Chlorine on the other hand, chlorine as we would find it on the periodic table, It's in group 7, so it has 7 valence electrons. We know that since this is going to be an ionic bond, that tells me that chlorine, because it has a change in electronegative value of 2, chlorine is the most attractive element here. It's going to be strong enough that it's going to pull that electron away from lithium, and that's going to form what's called a lithium. And we're not going to write down chlorine because lithium and chlorine, that'd be in essence that they have not bonded together, but these two have. So this would be a lithium chloride compound. All right, now we're not finished with this because what we have to do is we're going to figure out what our products of this are going to be. So our products, I know that these two things have combined together, okay? They bonded together. Well, our atoms, this is going to be the next column to our paper here. We're going to have atoms. We'll always put the metal first. So in this case, the lithium is first. We'll have chlorine a second. We're going to write down what the valence electrons would be. The valence electrons, I know we had 1 here. We had 7 here. All right, the transfer. This is going to be your next column, the transfer. The transfer, it went from the metal to the nonmetal. And then what type of ion did we form? Well, the lithium, we don't want to put Li. The ion that lithium is going to form is going to be a +1. Now, why +1? Because it got rid of a negative charge. It got rid of an electron, so it became more positive by 1. Chlorine, it picked up an electron, so it became more negative by 1. Now, these two values that I just wrote down, we have this +1 and the -1. Those are going to be the oxidation numbers that we're going to put right up top right here. We'll go +1, we'll go -1. Now, whenever you see a compound, you know that there's sometimes subscripts that we have to put in here. So we need to figure out what would be the correct subscripts for lithium chloride. Well, an easy way to do this would be just to crisscross these two values. So the -1, we got a 1 that would go down here. And then the +1, we'd come down here. Okay, and you're going to see that it would be a 1 to 1. As long as these two values right here at the top add up to be 0, there's not going to be a need to put any numbers down below. So you'll notice no numbers are needed at the bottom because it added up to be 0, so we don't have to put the 1s down here. And you'll notice that right here, for every 1 lithium, we needed 1 chlorine. Let's go to the second one. The second one, we're going to have our calcium. So we'll have calcium here. And let's say that we're going to bond this with oxygen. All right, we need to look at those electronegativities now. The electronegativities, calcium has a value of 1, and oxygen has a value of 3.5. We subtract these two, and you get a change in electronegativity of a 2.5. That tells me that this is an ionic bond that's going to form between these two. So calcium, and oxygen, we need to put in the valence electrons for this. So with calcium, it's found in group 2, so it has 2 valence electrons. Oxygen, it's found in group 6A, so we're going to have 6 electrons for it. So this is ionic, so that means that this electron here is going to be pulled away. Oxygen is attractive enough, it's going to pull that electron away and put it right there, and then the other electron is going to be drawn and pulled over and put right here to form a second pair. Now, what do we need to put down after this? Well, let's take and look at our atoms. We have atoms. We had calcium. We had oxygen. The number of valence electrons, we had 2 for calcium. We had 6 for oxygen. It went, for the transfer, it went from the metal to the nonmetal. What kind of ions did we form? We form a +2 ion and a -2 ion. So when we go to write out what the product is, we would have CaO. We're going to put those charges, the +2, we're going to put right up here. We're going to put the -2 right here. We crisscross the values. That would be 2. This would be 2. But you notice that they add up to be 0. So do you really need the 2's at the bottom? No, you don't. In order for this compound to form, since we have 2 electrons, since you have 2 electrons here that need to be lost and 2 electrons here that need to be gained, that means you only need 1 calcium per 1 oxygen. What compound did we just form? Well, we have calcium. We always capitalize that metal, and it always goes first. Oxide. The IDE tells me that this thing is chemically bonded with something else. Okay, let's go to our next example. Our next example, we're going to have beryllium. Beryllium is Be, and let's combine this with fluorine. All right, fluorine, that's that real attractive element on the periodic table. Most attractive element there is. In beryllium, it's not so attractive. Okay, so if we get our change in electronegativity, our change in electronegativity here is a 2.5. That tells me that this is going to form an ionic bond. So beryllium, that is going to be found in group 2. So it's going to have 2 valence electrons. Fluorine is in group 7A. So it has 7 valence electrons. Now, if we have this scenario right here, okay, I know that these 2 electrons need to be given away. Fluorine, what it's going to do is fluorine is going to take one of those electrons, okay? Now, fluorine can only take 1 electron. This fluorine atom right here, this guy, that thing is chemically stable. But beryllium, it has 1 more electron that it needs to get rid of. So if it has 1 more electron that is needed to be gotten rid of, and you only had 1 fluorine there, beryllium's not happy. So what beryllium has to have is beryllium has to have not 1 fluorine atom, it has to have 2 fluorine atoms for it to form a correct chemical bond. See, that electron is going to go down there to that fluorine atom. Now, let's continue here. Let's take a peek at the list on the right-hand side. We had beryllium. We have fluorine. Beryllium had 2 valence electrons. Fluorine had 7. We're always going to have a transfer from the metal to the nonmetal. So what type of ions are going to form? Beryllium needs to lose 2 electrons. Fluorine needs to gain 1. All right, so our formula, let's see if we did that dot diagram correctly. We put the metal and then our nonmetal. And now the charges, those oxidation numbers are +2. I'm going to put right here. And then our -1, I'm going to put right here. Those 2 values don't add up to be 0, do they? So we have to crisscross these. So the 1 is going to come down here. The 2 is going to come down here. All right. Now, since they did not add up to be 0, I need to have a 2 down here. Now, if you do just a little bit of simple math, look at this. If you have 2 -2's, doesn't that add up to be -2? -2 and +2, what do they add up to equal? 0. All right, and you're going to notice something. All right, you ready? If I have F2 here, how many F's did I have down here? 2. How many BE's did I have? I had 1. I have 1. Okay, so the last item of business that we have to have here is we got to name this thing. So with this one, you're going to have beryllium. And then we're going to put the last part. We're going to have fluoride. Now, why the IDE suffix? Because this thing has formed a chemical compound. All right. Next one, we have what would be the fourth one that we're looking at here. We're going to have anywhere from 10 to 12 that we're going to put in. All right, so our next one, let's say that you have magnesium. All right, you have magnesium and you have sulfur. First thing we want to do is we want to look at the change in electronegativities between these two materials. So magnesium and sulfur, we'll start with the most attractive. The most attractive is 2.5. Magnesium's is a 1.2. When we subtract these two things, you're going to notice something here, that our change in electronegativity comes out to only be a 1.3. So you might say, wait, a 1.7 is supposed to be the border for what would be considered an ionic. All right, now this would be considered a strong polar, but since you have a metal, metals want to give away electrons. Non-metals want to gain electrons. So this is going to form an ionic bond between these two. All right, magnesium. Magnesium has 2 valence electrons, so I'll put 1, 2. You're going to have sulfur. Sulfur is in group 6, so it's going to have 6 valence electrons, like this. All right, now, if we just do a kind of diagram showing these, our electron is going to come off the magnesium here, and then it's going to come off of the magnesium and go right here. All right. So on our list now, you have magnesium and sulfur. Magnesium had 2 valence electrons, sulfur had 6. The transfer is always going to go from the metal to the nonmetal. Magnesium is going to form a +2 ion. The sulfur is going to form a -2 ion. Now we need to get the name and the correct formula for this. So magnesium and sulfur, we'll put the oxidation numbers. You got the +2. You have the -2. Okay. Do we need to really crisscross that? No, because these two values right here, they add up to be 0. So there are no subscripts. All right. You need 1 magnesium for every 1 sulfur. The name of this then, you're going to have magnesium, and then we wouldn't write down sulfur, you'd write down sulfide. And you're going to notice I always put capital, lowercase. Okay. Next one, let's take a peek at potassium and fluorine. All right, potassium, K, you have fluorine, F. We need to look at the change in electronegativities here. Fluorine is that really attractive one, 4. Most attractive element on the periodic table. Strongest attraction between those. Potassium, not so attractive, only a 0.8. So the change in electronegativity here is going to be a 3.2, distinctively an ionic bond. Now, the Lewis structure here, potassium, it's in group 1, alkali metal, so 1 valence electron. Fluorine, it's in group 7A, so it's going to have 7 valence electrons. What's going to happen here? Since fluorine is attractive enough, it's going to pull the electron away, and it's going to form an ionic bond. We go over to our list. The list, we have potassium, we have fluorine. Potassium has 1 valence electron, fluorine has 7. It's always going to go from the metal to the nonmetal. We form a +1 ion, and we form a -1 ion. All right, we got to get the name and the formula now. The formula, put KF. I need to get the oxidation numbers, +1, +1, -1, -1. There's no need to crisscross because I can see clearly that these two values right here add up to be 0. I need 1 to 1 when we're doing this. Now, the name of this, you're going to have potassium. You don't change the name of the metal. And then for the nonmetal, we're going to have fluoride. So simple ionic bond is what we're looking at. Okay, next item. Next item here, you have aluminum, let's say. So if you have aluminum and you're going to bind this with chlorine, all right? So chlorine, fairly attractive. You got a value of 3. Aluminum, not so much. So what's the difference between here? Our change in electronegativity is going to be a 1.5. Okay, now you might say, wait, that's That's a strong polar covalent bond, but you got a metal and you got a nonmetal. All right, metals want to give away electrons, nonmetals want to gain electrons. So this is going to be an ionic bond here that's going to form. Aluminum is where it's going to get a little crazy here on us. I'm going to put this, we'll have aluminum. Now aluminum, it's found in group 3A, so it has 3 valence electrons. And I'm going to put them right like this. And then we have the chlorine. Chlorine is a halogen. It's going to be found in group 7A. So it looks like this. Now, when we do just a little diagram showing this, we know that aluminum is going to give away an electron, right? Chlorine only needs 1. So 1 chlorine to 1 aluminum is not going to be sufficient. You've got to have more than 1 chlorine atom to start with. So let's try 2. If you have a second chlorine atom here, that chlorine is going to have 7 valence electrons. So what we can have is, let's say this electron right here, it's going to come down. Now that chlorine atom is okay, but you're going to notice there's still 1 extra electron. You got this guy right here. So 2 chlorines for 1 aluminum is not going to be sufficient. So let's see, if we draw 1 more, will this work out? If you have chlorine, it's got 7 valence electrons. So let's take a look. We draw that over. And sure enough, now aluminum needed to get rid of 3 electrons. Each chlorine needed to gain 1 electron. So now we have the correct number of aluminums to chlorines. Let's fill in our list. You had aluminum, you have chlorine. We had 3 valence electrons for aluminum, 7 for chlorine. The electrons want to go from the metal to the nonmetal. The aluminum, if it gets rid of 3 negatives, it becomes more positive by 3. And chlorine, each time it gained 1 electron, it became more negative by 1. And we're going to put those oxidation numbers in. Right over here, you have aluminum and you have chlorine. Our values, you got plus 3. That means I'm going to have to put the 3 up top. I have the -1. I'll put the -1 here. Now these 2 values, they do not add up to be 0. They don't. So that means you have to crisscross these. So the 1 is going to come down here. The 3 is going to come down here. Now if you take a look, from that formula that we just did with those oxidation numbers crisscrossing, you can see here that you need 3 chlorines for every 1 aluminum. Just like the little diagram right there. Okay, we have to name this. We have aluminum, and then we have chloride. Aluminum chloride is what we're looking at. Our next one, let's take a peek at sodium and oxygen now. Sodium and oxygen. The oxygen atom, its electronegativity is a 3.5, so it's a pretty attractive element. Sodium, on the other hand, not so attractive, so it doesn't want to pull electrons to it. Makes sense because it's an alkali metal, and it doesn't want to give away it wants to give away electrons. So our change here is a 2.6. So that's definitely going to be an ionic bond that's going to form. Our Lewis diagram here, you're going to have sodium. It's in group 1, so it has 1 valence electron. You have oxygen here. Oxygen, it's in group 6, so it's going to have 6 valence electrons. Now, you should, by now, hopefully pick this up, that when you're looking at this, you have 1 electron that needs to be given away from sodium, but oxygen needs 2 for it to become chemically stable. So you're going to need to have a second sodium atom here, because that other electron that's needed for oxygen to be stable has to be pulled up like this from a second sodium atom. All right, now let's take a look at our elements. You have sodium, you have oxygen, 1 valence electron, 6 valence electron. The electrons are going to go from the metal to the nonmetal. If sodium loses that electron, it becomes more positive by 1. Oxygen becomes more negative by 2. So we'll have our sodium. You'll have the oxygen. We put those oxidation numbers in here. You got +1. You have -2. You can see that those two values don't add up to be 0, so you have to crisscross them. 2 comes down here. And what do we got? Na2, right? 2, 1, 2, for every 1 oxygen. All right, so now we have to name this. You're going to have, for the name, sodium oxide. That's what we're going to have for that. Okay, we're coming up on the end of this. You have, for this example, you have lithium and you have nitrogen that are going to combine together. We look at the electronegativities. Nitrogen, pretty attractive at 3. Lithium, not so attractive at 1. So our change in electronegativities for this is going to be a value of 2. So that tells me nitrogen is going to pull the electrons away from lithium. So lithium, it is an alkali metal, so it only has 1 valence electron, found in group 1. You have nitrogen. Nitrogen, it is in group 5. I almost made that mistake. Is in group 5, so it has 5 valence electrons right here. All right, so looking at this, lithium has only 1 electron to give away. Nitrogen needs 3. So how many lithiums do you think you're going to have for this? If lithium has 1 to give away and nitrogen needs 3, that means that you're going to need 3 lithium atoms in order for this compound to form. So the nitrogen is strong enough, it's going to pull the electron away from lithium. It's going to pull the electron away from lithium. It's going to pull the electron away from lithium. Okay. So on our list, I know that I have lithium and I have nitrogen. Lithium has 1 valence electron. Hydrogen has 5. We're always going to have electrons going from the metal to the nonmetal. We form a +1 and then a -3. So, writing our formula, that means you have LiN. The values here, I know that I have +1 for the lithium. That's our oxidation number there. You have a -3 for the nitrogen. These two values, they don't add up to be 0, so I have to crisscross the values and bring them down. So you're going to see that I need 3 lithium, 1, 2, 3, for every 1 nitrogen. We have to name this now. This would be lithium nitride, is what that would be. All right, we'll go to our next item. We'll have magnesium and fluorine that are going to bind together. Fluorine is that real attractive one, most attractive element on the periodic table. You have magnesium, not so attractive. When we subtract these, you get a change in electronegativity of 2.8. That 2.8 tells me that the fluorine is attractive enough, it's going to pull the electron away from magnesium. So magnesium, it's an alkaline earth element, so it's going to have 2 valence electrons. Fluorine is a halogen found in group 7, so it's going to have 7 valence electrons. Right off the bat, fluorine can only take 1 electron away. Magnesium needs to get rid of 2. So how many fluorines are we going to have? You're going to have a second fluorine in order to take that second electron away from magnesium. So this electron right here will be drawn to that fluorine, and this electron will be drawn to that fluorine. Okay. We have our list to fill out. You have magnesium, you have fluorine. Magnesium has 2 valence electrons, fluorine has 7. The transfer is always going to go from the metal to the nonmetal. The ion that forms is a +2 for magnesium and a -1 for each of those fluorines. When we write out the formula now, you have MgF, and we have to put those oxidation numbers in. +2, -1. These don't add up to be 0, so that means that I have to crisscross the values. So I see that I need 2 fluorines, 1, 2, for every 1 magnesium. So I did everything correctly. The name of this, you have magnesium fluoride, and we're all done with that. Let's go to aluminum. Let's say aluminum and oxygen are going to bind together with one another. Aluminum and oxygen now. Oxygen, pretty attractive, 3.5 electronegativity. Aluminum, not so attractive at a 1.5. So our change in electronegativity here is going to be a 2. That means it's going to form an ionic bond, just like everything else, right? So with this case, we have aluminum. Aluminum, it's going to be found in group 3. So it has 1, 2, 3 electrons here. All right. We have oxygen. Oxygen, it's found in group 6. So it has 6. 1, 2, 3, 4, 5, 6. Now you should notice something that's going to throw us off a little bit. Oxygen needs 2. Aluminum has 3 to give away. So let's see if we can do this part right here a little easier if we do the oxidation numbers and the crisscrossing first. All right, so I'm going to skip putting in those arrows and so forth until we do the other. You have aluminum, you have oxygen. Aluminum has 3 valence electrons, oxygen has 6. We need to have a transfer from the metal to the nonmetal. Aluminum, if it gives away those 3, it's going to be more positive by 3. Oxygen, if it picks up 2 more negatives, it becomes more negative by 2. So aluminum and oxygen, let's put those oxidation numbers in here. +3, -2. Those values, they don't add up to be 0, so you have to crisscross. The 2 comes down here. The 3 crisscrosses and comes down here. Now, let's use these values. We need 3 oxygens, right? So I'm going to put oxygen, oxygen, and we'll put those electron dots in here. There we go. And it says that I need to have 2 aluminums, and this is going to get real ugly. I wish I'd have done a better job at this, starting it out. So aluminum, it's going to have 3 right here. All right, let's try to fill in all of our arrows here. This electron is going to come here. That electron is going to come here. This electron is going to come here. Let's say this one is going to come down here to this. This one is going to come down here, and that one's going to go right there. You see how now all of the aluminum electrons, those 3 are gone. These 3 are gone. And I have formed what would be called an aluminum oxide compound. All right. Let's go. We'll do 3 more. I think that will get us to closer to the time of what would normally be a class, and it's still shorter than the other ones. Lithium and oxygen now. Lithium and oxygen. Oxygen, an attractive one at 3.5. Lithium, one of those ugly ones with an attractive value of 1. Once the metals want to give away electrons. Okay, so it's not going to be attractive. So you have a change in electronegative value of 2.5. Most definitely ionic. Lithium is going to give away its electrons to oxygen. So in our example here, we have lithium. It's going to have 1 valence electron. You have oxygen. Oxygen, it's going to have 6 valence electrons. Now, right off the get-go, if lithium has 1 to give away and oxygen needs 2, what does that tell you? You're going to need to have a second lithium atom here. All right. So why do I need a second lithium atom? Lithium has only 1 electron to give away. So that electron would be taken and given to the oxygen here. And then this lithium would give its electron to oxygen there. All right, writing down our information for our table, you have metal, nonmetal. Lithium has 1 electron in its valence shell. Oxygen has 6. The transfer is always going to go from the metal to the nonmetal. Lithium becomes more positive by 1 because it's getting rid of electrons. Oxygen becomes more negative by 2 because it picks up 2 electrons. All right, you have lithium and oxygen. We fill in the oxidation numbers, +1. You have -2. They don't add up to be 0, do they? So that means you have to crisscross. You need 2 lithiums, 1, 2, for every 1 oxygen. Last thing, we have to name this. So you have lithium oxide. All right, we're going to do 2 more, and then we're going to finish it up for the year.
Oh, yeah!
So the last 2, I'm going to start with the material, and then you have to finish it up for your paper, okay? So whatever I don't put in here, you have to fill in on yours. So you have potassium and sulfur. Sulfur has an attractiveness, not of 3, a 2.5, and then potassium a 0.8. We subtract these 2, you get a 1.7 for our change in electronegativity, so that's definitely ionic. All right. When we put in the symbols, you have potassium and you have sulfur. Potassium has 1 valence electron. Sulfur has 6. So right off the get-go, you should understand that since sulfur needs 2 and potassium has 1 to give away, that means that you're going to have 2 potassiums to start with. Okay. Just a little graphic on what happens here. Sulfur is attractive enough. It's going to pull the electron away from potassium here. It's going to pull the electron away from potassium here. Now when we fill in our stuff, you have potassium, you have sulfur. Potassium had 1 valence electron, sulfur had 6. The transfer is going to be from the metal to the nonmetal. Potassium will lose an electron, becoming more positive. Sulfur gains 2 electrons, so it becomes more negative by 2. Our formula, Ks, and we're going to put in our oxidation numbers, +1. You have -2. They don't add up to be 0, so that means you have to crisscross the values. You need 2 potassiums, 1, 2, for every 1 sulfur. All right, what do you have to do to complete this? You got to tell me what the name of it is. Okay. All right, we'll go to the very last one.
Oh, yeah!
You have magnesium and you have oxygen. You have magnesium and you have oxygen here. Oxygen, pretty attractive at 3.5. Magnesium, not so attractive. Okay, so oxygen definitely is going to pull electrons to it. And we have a change in electronegativity here of a 2.3. That means the electrons are going to be taken away from magnesium. And that makes sense. Magnesium wants to give away the electrons. All right, so magnesium, an alkaline earth metal, has 2 valence electrons. So I'll put 1, 2. You have oxygen. It's in group 6. So we're going to put in 6 valence electrons for it. Now, just a little graphic. This electron is going to be drawn here. That electron is going to be drawn here. So that's where the electrons are going to go, forming this ionic bond. All right. We have the magnesium, not potassium, magnesium. You have oxygen. 2 valence electrons, 6 valence electrons. They're going to go from the metal to the nonmetal. We form a +2 ion and then a -2 ion. What you have to do is you have to come up with what the correct compound would be. And let's say what the correct name of that would be. And with that, that finishes us up for the year. All you need to do is take a nice picture, try not to be sloppy with it, okay? Try to get a nice picture of what you just wrote down on your paper. Submit that thing up to Schoology and enjoy the rest of your time, maybe catching up with other classes, or maybe if you are all done, enjoy your summer. Just try to stay safe, okay? Take care.